Okay, good morning. Today we'll look at examples for chapter 5. There are a total of 5 example problems. First two are about adding and subtracting sinusoidal waveforms, meaning voltages and currents. Second two deal with components, inductors and capacitors, meaning 3 and 4. And then the last one is basically an entire circuit built of R, L, and C components. And then we apply a voltage and calculate the different quantities in the circuit. So we won't be able to get through all 5 today, but we'll be able to get done with the first 4. Okay. So get your calculators out, and I'm gonna go ahead and solve this as we go along. Okay, examples 1 and 2. Make sure I'm the right section, section 3. Let's look at the problem statement. It says Vs of t is given as the sum of 2 sinusoidal waveforms, 10 cos omega t plus 10 sine omega t. The question is not stated, but I will state it now. What is the value of Vs of t? That is the question. Okay, that is the question. So when we are adding or subtracting 2 sinusoidal waveforms, the first thing we have to ensure is that the frequencies are the same. And so if you wish to add or subtract sinusoidal waveforms or sinusoidal functions, the frequencies must be the same. If the frequencies are not the same, we cannot add or subtract them. Okay? The frequencies have to be the same. Go ahead and give you a real life example of where we actually add or subtract 2 sinusoidal waveforms. It's in every phone and every audio application that uses noise cancellation feature. It's a noise cancellation feature. Physically, there is a microphone present where your speaker is, and that microphone captures the surrounding audio signals, right? Surrounding vocals. It changes the phase of these captured signals by 180 degrees, and it adds them together. When you add them together, if it's opposite phase and the magnitude is the same, which is something like this. Actually, it's not quite the same waveform. It's 180 degrees out of phase. If you add these two together, the resulting value of the waveform is 0. And that's how noise cancellation feature works. There's a microphone that captures the surrounding audio signals, inverts the phase by 180 degrees, and adds that signal, so it's reduced to 0. So adding 2 waveforms, mathematically, what we're going to do is we're going to convert this into complex or represent it using complex numbers and then perform the math. Okay. As I said, first step you have to ensure is the frequency is the same. If you look at the frequencies, value is not given. It's simply listed as omega. So even though the value is not given, it is the same, and we can add them. Right? So first step, frequency must be the same. Second reason we can do this is because we are going to use complex numbers, meaning we are going to represent these as phasors, right? Phasors do not contain any frequency information. It's only magnitude and the phase angle. The frequency is irrelevant to a phasor. And since we are using phasor forms to perform this operation, we don't really care what the frequency value is. Actually, for the entire chapter, we don't really care what the frequency value is, because the frequency does not change. Okay. All right. So here are the steps. You want to find a value for Vs of t, which is given by 10 cos omega t plus 10 sine omega t. Frequencies are the same, so we can proceed. If we want to write the phasor, all expressions must be in cosine. So we need to change sine to cosine. Subtract 90 degrees from the sine wave expression and write out the phasor. What do you get? 10 cos omega t plus 10 cos of omega t minus 90. Sine x is equal to cos of x minus 90. It's a phase shifted waveform, right? Cosine is just a phase shifted waveform. So what's the magnitude and the phase angle for the first one? 10 with an angle of 0. Plus 10 with an angle of minus 90. Go ahead and perform this calculation on your calculator devices. And then let me know what magnitude you obtain. Let me know what phase angle you obtain. Again, every student needs to be an expert at doing this on your own devices. It's not just for electrical engineering. It will be beneficial for you in your own engineering fields. Anyone? Anyone with the final answer? Yes. You're talking about this one? It's 10 with an angle of 0 degrees. It's not 10 times. It's just, that's the format that we write a vector. Magnitude 10 with a phase angle of 0 degrees. So the question being asked is about this phasor representation. And again, it's easier. I mean, writing it out, it's not quite as evident or easier. The vector, basically, it's describing the two things for the vector, magnitude and phase angle. So it's describing the magnitude as 10, phase angle as 90 degrees. Okay, magnitude of the final answer. There's no penalty on speaking up. 14.14, absolutely. Anyone else? Anyone second or backs up that answer? I see one nod. I see one thumbs up in the far back corner. How about the phase angle? 45. That is incorrect. Negative 45. Yes. Attention to detail. As engineers, if you apply for a job, most jobs will say they want an engineer who has attention, who pays attention to detail. So plus 45 would be very different than minus 45. All right, so what I'm doing here is, since I am performing a addition of two polar numbers or polar coordinates, I'm going to convert it to rectangular coordinates so I can perform the addition. Again, if you have a programmable calculator, you do not have to show these steps. You can directly skip to the final answer. Again, if you have a programmable calculator or if you use an online software, you can straight away write the final answer. However, you better be confident in your abilities, because if your final answer is incorrect, then I would not be able to award you partial credit. Okay, yes. Okay, so the question being asked is how is the polar to rectangular conversion giving me these values, right? That's polar to rectangular conversion. So I'll go over the graphical explanation after I get done with this. Okay, so this becomes 10 minus J10. And then because we want our final answer in the time domain, the question being asked is what is the value of Vs of t? Vs as a function of time. So our final answer has to be in cosine. We have to perform an inverse phasor transform. So our answer has to be cos of omega t plus theta. To do that, we have to perform the inverse phasor transform. To do that, I need the polar coordinates. So my rectangular coordinates, 10 minus J10, I have to convert from, this is polar to rectangular. This is rectangular to polar. And 10 minus J10 gives me a magnitude of 14.14 with an angle of minus 45 degrees. All right, and my final answer would be Vs of t is Vm 14.14 cos of omega t minus theta, which is 45 degrees. Unit is volts. And that's your final answer. So always check the problem statement. If it simply asks you for the phasor form of Vs, you can leave it as that. But if it asks you Vs of t or I of t, current or voltage as a function of time, your final answer has to be as a function of time. Okay, graphical explanation. So rectangular and polar coordinates are simply the sides of a right angle triangle. So if you have, let's say, let's do this. Real axis, imaginary axis. Now, I have a vector that has a magnitude of 10 and a phase angle of 0. Remember, this is a vector that rotates counterclockwise, meaning if it goes counterclockwise, it's positive angle. If it goes clockwise, it's a negative angle. 0 degrees means where is my vector? It's lying flat on the real axis. So it's lying flat on the real axis with a length of 10. So imaginary component is 0. Hence, 10 angle 0 is 10 plus J0. Make sense to everyone? And then the second vector is 10 with an angle of minus 90. So again, to plot the phasor, you first look at the angle, mark out the angle, and then you just plot the magnitude. So in this case, the angle is minus 90. Where is minus 90? You have to start clockwise. Clockwise is negative. And counterclockwise is positive. So minus 90 is the negative imaginary axis. So I have a vector that lies on the negative axis. This is 10 with an angle of minus 90. The real component of that vector is 0. The only component is negative J9, negative J10. So this becomes minus J10. Sides of a right angle triangle. Okay. Then if you add these two phasors together, intersection point right there, splits exactly down the middle because it's 0 and 90. So minus 45, and then is the side of a right angle triangle. So 10, 10, apply the Pythagorean theorem, and you get the length of the hypotenuse or the third side of the triangle. Get 14.14. Makes sense to everyone? Let's take 10 seconds, think over that. Let me know if you have any questions. Any questions? Okay, proceed with the second one. Exactly the same procedure and the same steps. And let me know what values you obtain for the final answer. So again, I will solve it as we go along. I would advise or suggest to students that they solve it without looking at the screen. And so then once you get your final answer, just verify with mine. So we have V1 of t. One is sine, so you have to take, if you want to take the cosine, you have to convert it. Sine x is cos of x minus 90. Anyone with the final answer? What did you obtain for magnitude? Anyone? 29, yes. And how about phase angle? Again, if you're having, if you've never used your calculators for complex number math, again, there are resources online you can do. You can check them out, reach out to your peers, look at the discussion forum from the first week of class. lots of students who might be using the same make and model of calculators that you use. Yeah, hold on. Okay, so what was the question? Which angle? The final one or the... So this calculation I performed on a calculator. So this is from polar to rectangular conversion. And then from this one, rectangular to polar, also I performed on a calculator. But again, it's the sides of a right angle triangle, so we can just obtain it from there. The angle, the equation for that is tan inverse of y over x. So this is 22.8 is x, 19.14 is y. And so you can go tan inverse of y over x. And then the magnitude of the vector you obtain from Pythagoras theorem. So x squared root of x squared plus y squared, 29.77. So these conversions, again, at a minimum, if you take any scientific or engineering calculator, the polar to rectangular conversion and rectangular to polar conversion can be done using those. Manual calculations, again, trigonometric identities from the sides of a right angle triangle. Okay. X and Y, the the rectangular coordinates are the two sides of a right angle triangle. The magnitude of the vector is the third, the hypotenuse, and then theta is the angle. Does the method make sense? Any questions about the steps? Are we good? Proceed to number 3 and 4. Yeah. Writing down or question? Okay. And again, as I stated earlier, if you have a programmable calculator, you can skip directly from, let's say, which step? You can go directly from this step to your answer. Well, not that one. Here. Okay, because your calculators can add numbers in polar coordinates, so you can go directly. You can skip the 2 steps in the middle. All right. Okay. All right, example numbers 3 and 4. So the first 2 examples we looked at, we're looking at sources, meaning voltages and currents. Examples 3 and 4 look at components. We're looking at inductor in example 3 and capacitor in example 4, but the steps are exactly the same for both of them. Resistors behave the same way for AC as they do for DC. So we don't have to worry about those equations. For inductors and capacitors, if you wish to find, let's say, inductor current, then we integrate the voltage, right? IL is integral of the voltage. You have to perform differentiation and integration. But if you use complex number math, we don't have to do any of that. So in example 1, we are given the value of an inductor, we are given the voltage across the inductor, and we are asked to find the current. The phasor, as well as a function of time. That's already given to us. And then as a step in there, it's also impedance. We cannot solve this without finding the impedance anyway. Okay. So when you have this kind of expression, you have a voltage given to you or a current given to you as a time varying expression. The first thing you do is to compare it to the standard expression and extract the values for the three quantities, Vm, omega, and the phase angle. So 100 cos 200t, you can write the phasor for that. V phasor for that is 100, the phase angle of 0 degrees. And then Vm, the peak value of that inductor voltage is 100 volts. Omega is 200 radians per second. And phase angle theta is 0 degrees. So again, first step, compare it to the standard expression, extract the values of the three quantities, the peak value or the magnitude, omega, and then the phase angle. You write the phasor for the voltage, and from omega, you can write out the expression for the impedance ZL. Impedance ZL in rectangular coordinates is J omega L, is J times omega 200 times inductor 0.25 Henry. It gives you a value of J 50 ohms. You can also find the answer in polar coordinates. ZL in polar coordinates is simply omega L with the angle of plus 90. So 50 with an angle of plus 90. Then you simply apply Ohm's law. You can perform the integration if you want, but you can simply apply Ohm's law. So I can write IL is VL over ZL. So phasor for VL is 100, angle of 0. Phasor for ZL, sorry, not phasor, value. Magnitudes get divided, phase angles are subtracted. So it becomes 0 minus 90 . So it becomes 2 with an angle of minus 90. And then your I of t or IL of t is magnitude 2 cos of 200t minus 90. The frequency does not change. So when you perform the inverse phasor transform, you go back to the original voltage that's being applied and you use the exact same frequency. The frequency does not change. It is not affected. All right, questions? Do the steps make sense? Any questions? If you have no questions, you can proceed with this with the example 4. It's the exact same, except the equation for impedance is different because it's a capacitor. Yes. So the uppercase is representing the phasor form of IL. So the question being asked is, what does the uppercase, the lowercase signify? The it's actually not uppercase. It's a phasor. It represents the phasor for I of L. So it should be something like, I don't know. I never figured out a good way to write out the phasor for quantities, except put a little bit studs at the end of those letters. Okay, example 4. Go ahead and solve it while I solve it on the screen. ZC is 1 over J omega C, or 1 over omega C with an angle of minus 90. Remember, current for a capacitor is always ahead of the voltage. So theta V minus theta I will always be minus 90 for a capacitor. Impedance for a capacitor is always minus 90. Magnitude 2 with a phase angle of plus 90. Exactly the same steps. You first take the voltage, you find the impedance of that capacitor. Remember, impedance is a function of the frequency. So depending on the input voltage or the input current, the impedance will change. So you have to have the omega frequency information. Then you plug it in, calculate the impedance, then simply apply Ohm's law and solve. Final answer asked in phasor form, you can simply leave it at magnitude and the phase angle. If it asks you as a function of time, then you have to perform the inverse phasor transform. And that's it. All right, questions? Okay, we'll end class here today, and we'll pick up here on Wednesday with example number 5. I will be in my office later this afternoon. If students have any questions, feel free to stop by.